Hello and welcome! In this first video, you will see the principle of repetition and series through the creation of some algorithms on Grasshopper. As it should be already known, what is presented during this and the next lecture can be extended or modified at will and also be integrated with other algorithms in the generation of more complex solutions. Furthermore, what is proposed are only examples that can be written in more or less compressed forms and with more or less different logics depending on whether, for example, you choose a more geometric, mathematical or a specific logical approach or a mix of these. The algorithms and logic presented will also be applied and adapted to some case studies on which it will be possible to visualize the results, finally arriving at the so-called bake of the results obtained. Regarding the theme of repetition and series, during the course, different interpretations of the topic will be presented. Specifically, two many types of series will be shown: the linear series along a straight line and the linear series along a curve. Of these repetitions, some variants will be proposed, taking advantages of example and case studies in which the application of these generative principles will be shown. The case studies considered are the following: Fondazione Gian Giacomo Feltrinelli building in Milan by Herzog De Meuron and the Sirocco temporary installation in Helsinki by Kivi and Tuuli Sotamaa. Let's proceed with the first case, the linear series of a portal, and see how the algorithm that defines its principle can be generated. For this case, a point was first generated with a construct point node of which the x, y and z positions were defined through the number slider. This set of nodes was then repeated 4 times until the 4 vertices of a portal were determined. These 4 points were placed within a single dataset through the merge node. To define the profile of the portal, they were then subsequently connected to the polyline node. The order of connection to the merge is in this case important to define the correct generation of the portal lines. Through the linear array, the repetition was then defined by specifying the direction vector, in our case the y vector and the relative number sliders that defines the distance between one repetition and another. For the count item, the number of repetitions including the initial starting one are defined. Through sweep 1, the three-dimensional shape of this portal was then defined by adding a circle to this section's entry that can start either from the initial or final point of the polyline. You define the geometry you want to have, in our case circular, and which must be defined in its radius. If a polygon node is connected to the sweep 1 node instead of a circle, you can define profiles with triangular, square, pentagonal geometry and so on, depending on the value set in the segment's entry. As an example of a linear series, we propose the Fondazione Gian Giacomo Feltrinelli building in Milano by Herzog De Meuron. The logic behind the algorithm is the same as the one proposed, with the difference that the structural elements in elevation in this case were not defined by points, but by closed profiles, and that these were previously rotated before their repetition in series. While for the horizontal planes, these were simply extruded. In this other animation, we started from a geometric portal shape previously defined and modeled in Rhino and referenced on Grasshopper through the geometry node. As in the previous case, the shape has been inserted into a linear array also here defining the vector and the repetition distance as well as the number of these. Notice how all the repetitions with the rotate node can be rotated according to specific angles. If you wanted to rotate them progressively, just define a range of values expressed in degrees by a number slider and convert it with the radians node connected to the domain of the range node. If the same variable used to define the number of repetitions of this series is used at the input of steps of the range, this geometric operation is applied with progressive values for each element of the repetition. Notice also how an x-1 expression has been applied to the steps value of the range. In the plane item of the rotate node, it is possible to insert a rotation plane. In this case, an xz plane was used, but it can be changed as desired and an origin point defining the origin item. A variation of the linear series is to modify the geometry of a portal by introducing here also progressive change between the components of the series itself. By taking one of the algorithms already illustrated and breaking it immediately after the merge of the points, this additional functionality can be added. The linear array node was also deleted and will be replaced with another way of creating repetition, as we will see shortly. Specifically, to reproduce the linear array in another way, a move was added after the merge, setting the y direction as the repetition axis and adding a series node to the factor with a fairly high indicative number of steps. In our example, we took 370 and the number of counts equal to the number of repetitions that we want to insert in our series. Subsequently, we add a flip matrix to the algorithm chain, from which we start two connections, one to a replace item and one to a list item. To the latter, we add outputs until we reach 4, and which will correspond to the 4 points of the portal. Now we can take the second point indicated with a +1 entry and connect it to the geometry set to flatten of the move node, and which will be connected to the item entry of the replace item in graph mode. The motion voice of the move will be connected by a vector xyz node, and each of its inputs will be connected to a range node with an x-1 expression applied to the steps and connected to the same count variable as the series node. As the domain of the tree range, we define three variables that will correspond to the maximum movements along the tree direction x, y, and z, and that will occur proportionally between the first and the last point of the repetition. Finally, we connect the replace item with the polyline to connect the points and give them three-dimensionality. If you want to create a series along a non-linear path instead, you can proceed as follows. We can reference on Grasshopper a curve previously drawn on Rhino on which we want our series to be distributed. We divide this curve with the divide curve node by setting the number of subdivisions that we prefer to the count input. For each of the points created, we connect a circle node setting the radius we want. With extrude, we give three-dimensionality to the circles by adding a vector on the z-axis with a factor value set to the amount we want to extrude in height. An example of application of the principle of this algorithm can be observed in the Sirocco Temporary Pavilion installation in Helsinki by Kivi and Tuuli Sotamaa. As can be seen from the animation, the possibility of progressively defining the heights of the various repeated elements as well as their rotation has been added as a variant. The same algorithm was then replicate it for each curve that defines the installation. What has been presented in this lesson, first of all, shows the basis for the generation and application of the principle of repetition, defining one or more logics that are explained in different algorithms, each one created or adapted to the purpose that was set. Secondly, it shows how the same principle can be formally expressed in ways that are also totally different from each other, even if there is the same underlying logic behind it. Thanks for following this unit and good work!